My name is Doug Innocent, and I am a graduate student of the University of Florida. I'm currently working to finish my master's degree in structural engineering, while simultaneously working as a graduate research assistant. As a research assistant in the structural engineering group at UF, I have been assigned to a project with the Florida Department of Transportation designing highway breakaway systems for my thesis. It has been a long 2 years, but thanks to the phenomenal mentorship from my advisor, Dr. Gary Consolazio, and a little elbow grease, I've been able to complete a very cool project. Video editing is a hobby of mine I picked up when I was younger. So today, using my video editing skills, I'm going to present my thesis in a way hopefully you have never seen before. My plan is to walk you through the design process from development to final testing. I'll be here in the background to provide clarification and walk you through some of the concepts. I want you all to be engaged, so I'm going to turn the volume a little bit. Alright, let's go. Breakaway sign systems can be found on highways throughout the nation. Here in Florida, these systems must be designed to withstand 150 mph winds while also breaking away in the event of impact with small vehicles. Design control specifications set forth by AASHTO-MASH require that these systems break away under impact speeds as low as 90 mph. Due to a recent policy change made by the FDOT, breakaway systems currently used on Florida highways designed for a 50-year design life have been requested to be redesigned for a 10-year design life. Subsequently, the purpose of my thesis project is to optimize, simplify, and redesign a breakaway system for a 10-year design life due to this new policy change. Finite element analysis is a cost-effective tool that has been used to design the breakaway systems presented. Through these simulations, components such as the shear control moment collar and the fuse plate hinge plate connection have been optimized and designed. The results of the finite element numerical simulations have given insight into the proposed system behavior. Advanced multi-physics software LS-DYNA has been used to run these finite element simulations. The first step in the design process was to develop a system with adequate structural capacity against 150 mph resultant wind loading. Finite element quasi-static pushover analysis served as a great tool to evaluate the structural performance of the system. The design of the breakaway systems was an iterative process. The focus was to develop a system that was lightweight and easy to assemble. The shear control moment collar is designed to clamp down on the breakaway system's flange plates and resist moments that develop as a result of wind loading on the upper post. The two collar halves are held together by 4 bolts, 2 on each side. These bolts fail in tension during impact loading. The fuse plate and hinge plate connection is located directly under the sign panel. The fuse plate is perforated by 4 1-inch diameter holes to weaken the tensile strength of the plate. During impact, the fuse plate ruptures and the hinge plate allows for the impacted post to rotate out of the way of the vehicle while also keeping the upper post from falling onto the vehicle during the impact event. At the final rotated position, the hinge plate holds the detached post leg in place and keeps the post leg from rotating back into the impact zone. The fuse plate and hinge plate have been designed with the capacity to resist 150 mph wind loading. I hope you all are still with me because it's about to get really good. The next part of the design process consisted of experimental physical testing. Physical testing was conducted to validate the results of the finite element simulations. For the wind loading case, static flexural tests were conducted in the UF Structures Laboratory. The breakaway system was positioned horizontally and progressively loaded with a hydraulic jack to imitate resultant wind loading. The system response was monitored as loading was applied until the ultimate capacity of the system was reached. The results of the flexural test confirmed that the proposed system maintained adequate capacity, exceeding what was needed to survive the design wind loading. To evaluate the breakaway performance of the system under impact conditions, dynamic physical tests were conducted at the Florida Department of Transportation Structures Laboratory using a gravity pendulum facility designed by Dr. Gary Consolazio and Dr. Longbilly. Evaluation of the breakaway systems required multiple tests. To make this possible, a cost-effective surrogate vehicle designed to recreate the crush behavior of a MASH-compliant Kia Rio, also known as the UF FDOT crushable nose, was designed by Dr. Gary Consolazio and Matthias Gruters. For impact with the breakaway systems, the crushable nose is raised to a 12-foot drop height and released. After release, the potential energy stored in the crushable nose was converted into kinetic energy, allowing for initial impact velocity of 19 miles per hour to be reached. The force deformation behavior of the crushable nose was controlled by an 1100 kilogram concrete mass in addition to the deformation of aluminum honeycomb cartridges shown in these compartments. Aluminum honeycomb is a low-weight, high-strength material. At a given crush load and material strength, this unique material deforms in a predictable manner. By adjusting the overall cross-sectional area of the aluminum honeycomb cartridge, the force deformation behavior of the cartridge can be controlled. Aluminum honeycomb cartridge tests were fabricated and tested in rigid impact, for comparison to production vehicle rigid impact tests provided by the National Crash Analysis Center. Results of the rigid impact test validated that the force deformation of the crushable nose closely agreed with the test curves of the MASH-compliant key area. Due to cable interference, a full 3-post system was not able to be tested with the pendulum. Therefore, a comparable single-post test was designed and conducted. The physical tests were compared to single-post FEA impact simulations and confirmed that the FEA adequately predicted the behavior of the breakaway components. The data processed from the accelerometers placed on the crushable nose demonstrated great results far below the maximum occupant risk limit set forth by ASTRO-MASH. For the fuse plate and hinge plate connection, an alternate single-post physical test was also developed. Similarly to the breakaway component impact test, the results demonstrated the aptitude of finite element simulation to accurately predict the behavior of the physical system. So, there you have it, my thesis project presented in a way hopefully you've never seen before. When I started this project, it was just a big idea represented by calculations on engineering paper. So this is just a reminder to give our thoughts value and to trust in our power of creativity. We can do anything we put our minds to. The trick is to break it into very small steps.